Good afternoon, everyone. Thank you for attending today's webinar. Shauna will be covering continuous installation for residential construction, part two. So we did another session in January that covered part one. So that's posted on the recording platform. So you guys can always go back and watch that if you're jumping into part two without that context. But if there are any issues with audio, feel free to write me in the chat. My name is Erica DeLello. I'm a senior project manager for Noresco. This series is sponsored by the Colorado Energy Office with training materials created by Noresco. All right. So Shauna and I have been working with the Colorado Energy Office for years now, providing trainings just like this one. This is a webinar starting our new series that'll go through the end of this year of Wednesday webinar series. Our next one is covering a lot of the resources, the new resources that we've put together. So definitely take a look at that as well, and a bunch of other great topics on the docket for this year. We do also have a new series covering the low energy and carbon codes R408 section, so the additional efficiency requirements and how they differ from the 2024 IECC. So if you're curious about those changes, it's a two-part series. It starts at noon and it's on Thursdays. And then we are working on an on-demand platform. I'm hoping we'll have something launched by the end of April, but we shall see how that all flushes out. But of course, there's always all the recordings from all of our previous trainings. If there's a topic you guys are interested in, definitely check that out. Okay, so we're coming up on a deadline for technical assistance for code adoption. If your jurisdiction is thinking about adopting codes prior to the June 30th deadline, definitely reach out to us. We offer free technical assistance for code adoption, but we're hoping we can get any inquiries as soon as possible. So to make sure that we're able to complete that adoption before the 30th of June. Okay, so then we've got a whole bunch of different resources. There's a lot of resources on the Code Adoption Toolkit that you guys can check out. I'm only listing like a small portion of them right here, and a lot of them are focused on the low energy and carbon code. If there's any specific questions about what you need in order to submit for the low energy and carbon code as jurisdictions adopt the LECC, definitely reach out. We are putting together an instruction guide for that too. All right, and last but not least is the Colorado Codes Helpline. This is a great resource for all of those in our state or completing projects within our state. You can submit a question on any of the I-codes, and a subject matter expert gets back to you within a couple of business days. So definitely utilize that. And yeah, all right, let's see. I'm going to go ahead and stop sharing my screen, but throughout today's webinar, we do want to encourage questions. You have the ability to write in the Q&A or raise your hand. I'll probably, depending on your timing, Shauna, or I think, maybe if you could stop in between slides at one point, see what questions we have, that'd be great. Otherwise, I'll hold questions to the end to make sure we can get through all of today's content.
Perfect.
And with that, we'll pass it over to Shauna to take it from here.
Marvelous. Thanks very much. Yeah, I saw somebody ask if we could put the link to the video, the first part one in there.
Oh, cool.
So,
yeah, I will get that posted in the chat.
yeah, so we'll talk about part one a little bit. Maybe let's just go into that right here. So I'm Shauna Mozingo, Codes Project Manager with Noresco, and so happy to be here again for our webinar today. We are going to go over a few things from the first webinar, and then we're going to jump into the questions that you all sent from the first webinar. Some of them around fasteners, maybe a little bit of revisiting of the fasteners. We're going to go into dew point calculations and double wall construction, and thermal bridging. Those all of these seem to be questions that came in, and so we just want to make sure that we address them all today for you. If you have more questions, please put them in. I sent out a ton of resources after the last webinar. You'll get some more today. So once this webinar gets finished, I will create a list of resources for you and send them to you with this presentation. So that you'll have it and you'll have the links. But one thing, if you want, in the meantime, as I go through the slides, I often put a link of where I got some information or some helpful information. Just take a picture of the screen so that you have that link, because there's some really great resources in there. All right, let's get going. Let's get just a review, right? A review of last webinar, part 1. We're not going to go into too much detail on this. This is what you can look forward to in part 1 if you haven't seen that one yet. It's just why continuous insulation. And as I say continuous insulation, I just don't want you to picture in your head rigid foam board. That's one way of doing continuous insulation. There's a lot of different continuous insulation. I'm not here to support one industry, right? I'm just talking about continuous insulation as a code requirement and as a code option. So definitely energy efficiency. We can see the energy efficiency, the thermal bridging that takes place, the thermal benefits, holding the heat inside the house if we're trying to heat the house, keep holding the heat outside the house if we're trying to heat or cool the house. Right, code compliance, whether we are doing a prescriptive R20+5 or if we're doing a trade-off path where we're going to get more benefit for having that continuous insulation on the outside or the inside of the wall. Thermal bridging, we're going to talk about in some more pretty good detail today because that was requested. So I'll just leave that up there. Reduce moisture damage, improve building durability. We're going to talk about that as we get into vapor and dew point and that sort of thing. Definitely continuous insulation serves a huge role in all of that. Enhanced comfort, right? If we have continuous insulation together with our tight houses and great insulation, we have more comfortable houses. We have houses that hold the heat a lot longer. If we're trying to heat a space, it stays the same temperature a lot longer. And so we are a lot more comfortable. We can shelter in place if an emergency happens. There's all kinds of benefits for that. And then I always like to mention this as the codes start progressing and as jurisdictions start progressing towards either the state minimum of electric ready, but we're with a goal at some point for building electrification for some people. You have to start with a great thermal envelope, right? We want to build this really great thermal envelope, and continuous insulation plays a huge role in that, so that if we build a great envelope and we reduce the amount of loads inside the building, then we're not taking as much loads over to the grid, and which seems to be everybody's panic point is, what are we going to do to the grid? And so how we build our buildings has just as much to do with that as the electricity itself. So those are some things that we touched on in the first. The second is this idea of using one product or one thing for multiple benefits, right? This is more in line with rigid foam board type of materials, but right, you can have one product be your water control layer, your water resistive barrier, your air barrier, your vapor control layer, and your thermal control layer, right? Doing that insulation and thermal bridging. So we talked a lot about that, and I just like to bring that back around because we get a lot of time people saying the cost of continuous insulation is too much, but when it can take the place of 4 different you have one product that's serving 4 purposes, if installed correctly, of course, then maybe that takes away some of that cost conversation. also wanted to bring this back. We talked about all the different kinds of continuous insulation, and somebody had submitted a comment that I had my R values incorrect. And so, for XPS, the extruded polystyrene, at R5 per inch, EPS at 4.6. And so I had all of these R values listed. Somebody said maybe check them out. And I went back to each of the manufacturers and to the different products. And these are the values that I'm finding consistently. So I would love to hear from you if you're seeing something different than an R5 per inch in XPS average. This is, about an R4.6 per inch in EPS, and about an R5 in the GPS, polyiso 6.5 to 7, and then 4 to 4.3 in mineral wool. So if you're seeing something different, let me know. I would love to see that so I can reach out to the manufacturers and see what's up. So, but just remembering, a lot of these are your rigid foam boards. You have mineral wool that we're going to start seeing a lot more of as we move into wildfire resiliency and different things. So it's not that you have to do that, but we're going to start seeing it more and more as people choose different ways to get that resistant construction. But there are a bunch of other ways. Real quick, I want to stop because it seems like there's something in the chat.
Yeah, we've got a question about, we often see EPS insulation recommended as sub-slab insulation, but you indicated in part 1, if it gets wet, it retains moisture and water. Which type of insulation would be optimum?
Yeah, that's great. So remember, and I didn't go through these in detail this time because it is in part 1, but so there are some problems like when you talk about XPS and then I think it is GPS. Where it's slow to release moisture. So it works really good for a while, but it holds its moisture and it's slow to release it. So it degrades over time. And the what we're finding is that the manufacturer warranties don't last as long. And so they won't warranty for 100% of the R value over time. They reduce it, they decrease it over time. So that's for XPS. EPS, though, it says retains its R value over time. So if you're seeing EPS in the foundations, that's great, right? So it does retain its R value over time, and it can be used anywhere in the envelope. So I think that is, if you're seeing EPS, that's a good insulation to see. So I'm sorry if in the first one I said EPS didn't, because it's mostly XPS and GPS that sometimes lose their value over time. All right. All right, so some other ways of continuous insulation, double walls. We're going to talk about that because we had a couple people ask for double wall requirements. So we're going to look at that. Bats, yes, you can have bats be continuous insulation. Remember, it's not the type of material, it's how it's installed. You can have a bat hung on a wall continuously, like you see a lot in basements, right? Or sometimes in crawl space walls. And so that would be a continuous insulation of a bat versus a cavity insulation where it's installed between two framing members. And so, yes, you can have bats done. Spray foam, a little bit harder because you're going to have a cavity, you're going to have a cavity, at least you're going to fill the cavity with the spray foam. And then in order for it to be continuous, you would have to go over the top of that framing. And that's going to be a little bit harder to do, especially if you're trying to close something in. So spray foam is probably one of the insulations that I don't see used continuously in a lot of places, maybe in an attic. Wood fiber board, we're starting to see some of that as we get into different, more sustainable type of construction where it's just taking this wood fibers, this chips that are left over from lumber production and refining them into a fiber, adding some borate, which makes it a flame retardant, resistant to mold, mildew, those kinds of things. So we might start seeing a little bit more of that. And then what are some other things? Some other things might be SIPs, right? Structural insulated panel wall construction. We can see that sometimes used as continuous insulation values. We can also see insulated concrete forms where we have the insulation and then pour the concrete, in between, but with some plastic, usually plastic or less thermal bridging type material used in there. And so you can have continuous insulation. There's a lot of ways to do continuous insulation. One of the problems that I see often are when people say, well, I don't want to do continuous insulation, mostly thinking of rigid foam board, right? On the exterior, I don't like all those details. It's hard to install. There's some things out there I just want to remind you of. In the 2024 IRC, the residential code, Jay Crandall with, he's a consultant he worked for a lot of people, but he and the American Chemistry Council, they got together and with somebody, Rob from DuPont, and they put in this proposal that made it into the code. It's in Appendix BN, which is this extended plate wall construction. It's kind of, even Jay will tell you, yeah, there are some, there are a couple of things that we need to work out that we have to figure out, but it was a good place to start to just kind of give you the idea of how you could construct a house with continuous insulation without having the crazy, issues at windows and doors and openings. So it basically it's this concept. You have to have a double top plate. For sure, it's limited to 2 stories. Let's see, 1 and 2 family dwellings, townhouses, and no more than 2 stories above grade, and seismic design category A and B. So there's some limits to it, but it's basically I have a 2x6 plate and a 2x4 wall. That way, and then I have a couple inches of insulation, right? And so this all is. It's a 2x6 wall, but with only 2x4 construction and then the insulation. So that's one way of doing it. That's trying to bring some type of prescriptive requirements for continuous insulation into the code for framing. So it was a good approach. There are, like I say, it's pretty limited, and I'm sure it will expand over the years. It looks like this, right? You have this 2x6, like I said, the 2x6. You have 1 bottom plate, but you have to have a double top plate. It's 2x6 with the 2x4 wall and then the insulation. That's just one way of doing it. You're going to find all sorts of different ways to do it out there, but it's nice that the code is trying to go there. It's hard to write something prescriptive like that because then it's very limiting. All right. The other question that I had come in was not necessarily a question, just a statement, like, can you go in a little bit more, can you cover the fasteners again? What's allowed and what's not allowed? Well, you can pretty much do anything. It's just, can you call it continuous insulation after you're done? Right? So we look at the definition in the code of continuous insulation. It's insulating material that is continuous across all the structural members, right? So it's not in a cavity. You have framing and you install the insulation continuous over it or over the top of your concrete walls. So it's continuous across all the members without thermal bridges other than fasteners, right? And service openings. It's installed on the interior or the exterior. All right, so then we get into this. What is a fastener? Fastener is like this point thermal bridge. You might have some thermal bridging right here, but it's just a small point. And overall, that it's calculated into the U factor of this wall when you talk about like if you're putting something into ResCheck or ComCheck or something like that, it's calculating the small thermal bridging effects of fasteners, right? So it's a nail or a screw or a clip or a bracket or maybe like this hat channel, right? So I have this small thermal bridge here, whether I'm going through my cladding, through the insulation, into the framing. This is metal framing, just as an example. I'm going through something at a small point. It's not hugely continuous, right? Or I have a hat channel in here where I have my insulation. I'm attaching my insulation to the framing. I put my channel up and I'm even though this is metal, I have my cladding going into the metal, but I don't have a continuous bridge from the cladding all the way through to the insulation, right? Because they're being connected at different points. So a fastener or a screw is, while it is a point thermal bridge, it is allowed to still be to attach your product and have it still be called continuous insulation because you're limiting amount of that thermal bridge versus something like this where you have this a linear thermal bridge for cladding supports like these Z channels, right, that now form this line all the way up and down the building. And so you now have this linear thermal bridge. So continuous metal or wood frame that penetrates the exterior insulation layer, creating a cavity. Something I just want to point out on this, I didn't point out last time, was that a lot of times I get questions from people saying, hey, the jurisdiction turned me down for my ComCheck or my ResCheck because I use these Z channels or, whatever you want to call them. And so they're saying I can't count that. How do I do this in ResCheck or how do I do this in ComCheck, right? Well, you can't. So if you're familiar with ResCheck, and I just talked to Rob Salcido with PNNL just this morning to just make sure. If you're familiar with those softwares, it allows you to enter a continuous or a cavity, but it doesn't allow you to enter two cavities or two continuouses, right? And so what you would have to do is go and call it other. If you had a cavity plus a continuous. If it was just cavity, if this was the only thing you were doing was this insulation on the outside of the building with this, then you would call it a cavity insulation and you just give it the R value for the cavity insulation. But if you had this on the outside plus a cavity insulation on the inside, how do you calculate that? Do you add the two cavities and call it, whatever? Maybe you could do that, but the best way to do it would be to take some of these wall calculators, these R value and U factor calculators, put in every layer of the assembly and come up with the U factor for it. You could do, when I was talking to Rob, he said, you could use like the RemRate or Ecotrope or one of those performance softwares to calculate the value and use that and put into ResCheck if you were going to submit through ResCheck or ComCheck. There's different ways to do it, but you would have to use other and calculate the U factor of the entire wall and put that in there because it doesn't really allow you to have two cavity insulations, one on the interior and one on the exterior. I told Rob, and he said he was going to look at trying to add more options into ResCheck and ComCheck to make sure that we could have more flexibility with all the different kinds of walls that we're starting to see. And he's going to look at for me to see if adding this external U factor plus the internal U factor could, or external R value for the cavity, internal R value for the cavity, just add them together, the two layers. If you could do that and how much difference it would be, I think it's really going to be dependent on how that wall is made, what it's made out of. So I think for now, if you're seeing this kind of insulation on the exterior of your wall where it's making a cavity, you would need to use other NRES check. Otherwise, just go performance would be your best bet. All right, so also reminding you that the IBC does cover fasteners, telling you that Z-fring penetrating through exterior insulation makes it cavity insulation. It's not just an energy code thing. It's not just a insulation thing. The building code also talks about it. And there's more information at continuousinsulation.org, which, you know me, that's one of my favorite websites. They have so much information there. So if you want a really detailed report that the foam sheathing folks put out on fasteners, there's this great report here. You can take a picture of this, or it'll be in your resources that I send out. But they did a good detailed report on the different kinds of fasteners, the different kinds of thermal bridging that happens, how to calculate that into your U factor of your wall, and that sort of thing. I don't really have a ton of time to go into it. All right. The other thing that I did find interesting was just a reminder about tapes. You know, if we're going to use this one product, like say a rigid foam board as a continuous insulation and a weather resistive barrier, air barrier, vapor barrier, all of the things that we want it to do, you have to seal all the joints and seams. And so different manufacturers of different insulation call out different tapes or different things. And so one thing, I see a lot of black tape when I'm going around, and just, you know, this is in that same report on the fasteners, but it was interesting to see that those butyl tapes are vulnerable to temperature, UV light, and chemical exposure. And so the better tape is acrylic tapes that are resistant to those things. So again, more information there, but just something to point out. Let's talk double walls real quick. Double walls is a way of doing continuous insulation, right? So wherever we have wood, we have about R1 per inch. And so we put continuous insulation over the top of that to not have such thermal bridging right there, right? Wherever the studs are. And so how do we combat that? Well, yeah, we can put that continuous insulation, or some people are not wanting to use continuous insulation for various reasons. And so some people will build double wall systems. There's a couple different ways to do double wall systems. There's a bunch of different ways, actually. But one of the ways is to build, like, I have an interior structural wall, and so I build a secondary exterior structural wall. They're both, you know, a lot of different ways to do it. In this picture that I got at Building America Solution Centers, good resource. You know, they have cavity insulation on the interior wall, cavity insulation on the exterior wall, but also a layer of rigid board or a layer of continuous insulation, right? And so that continuous insulation is taking up the thermal bridging that would have happened between all of these wood studs, right? Or you could do it the opposite, right? You have your structural exterior wall and a non-structural interior wall, but you have a layer of continuous insulation in there. Another way to do it is to have your framing lined up so that you have double walls, but you offset them. There's a bunch of different ways to do it. I have this really amazing video that I'm going to play for it, but I don't think you're going to get sound. So we were testing it earlier. I don't think you're going to get sound, but maybe I can talk to you a little bit about it. So this is a cool video from Building America that I found on Building America Solution Center with a good process or a project in here, or a process of insulating. You can't hear this, right, Erica?
I can't.
Okay, that's fine. That's fine. It's just, he's just explaining this double stud or double wall system that they're using, and I will narrate for you as we go through. So let me get inside the wall. There you go. So what they're doing is taking like some rock wool insulation and insulating this exterior structural wall. So they have this exterior structural wall, insulating the cavities with rock wool, which is about an R15. This is an old video, right? And so that's okay. Then they take a 2-inch thick layer of rock wool and add it continuously on the inside of that wall. So now you have a cavity plus a continuous insulation right here, right? And so you break up all that thermal bridging. I'm just waiting for them to get a little further here. Sorry. Right. So the middle layer is probably the most important layer of the wall because it does that thermal bridging effect. It mitigates that thermal bridging. So, and you can see rock wool being used is going to be a good way to deal with your wildfire. Then they use a smart barrier. So this is like your vapor retarder, but they're going to put it on the interior non-structural wall, but on the exterior side of that interior wall. So you have this smart barrier that, depending on the time of year, will let the vapor out, right? And if it gets in. So that's kind of a cool thing to do. If you haven't seen those smart barriers, I would look at it. But so see, you have this interior wall, and they stand it up next to the exterior wall, and now you have a cavity insulation, a continuous insulation, and your vapor and air barrier. And then you have an interior wall that all your plumbing and your electric can be installed in, right? And so that's nice because then you don't have to worry about any penetrations to your thermal envelope. So that's kind of another way to do double wall systems, as opposed to this one, where you can see, okay, I have this double wall. I've kind of offset the studs, but I have this double wall where I have a structural wall and then an interior wall. But I don't have room. I have no vapor barrier, air barrier, or no room for a continuous layer of insulation inside there. So maybe not the best way. The best way is to build that structural wall, get it all done, and then put your interior wall in if you're going to do it that way. So there's a bunch of different ways to do it. Somebody just asked if I would cover some of those, and I think that if you want to go to Building America Solutions Center, there's a lot of great information there. The National Association of Home Builders put on some really great videos on how to do double wall systems too, and count it for continuous insulation. So that's another good resource for you. What do we have? Do you calculate EPW construction similar to standard exterior insulation, where the insulation covers all the exterior sheathing surfaces? So there's a question. I'm going to cover it right now because it's in here, right here. Exterior plate wall construction. Do you calculate exterior plate wall construction similar to standard exterior insulation, where the insulation covers all the exterior sheathing surfaces? I would imagine so, because it is continuous insulation on the exterior. You have a cavity plus a continuous. I'm guessing maybe I'm not understanding the question for sure, but you have a cavity plus a continuous, so you would be able to count that exterior one as continuous insulation. No, not 100%, because you have a 2x4 stud wall, and then the continuous insulation. So that insulation is covering all those studs. And I don't know if that's what that question is meaning, but that's how I'm taking it. All right, let's go through here real quick. All right. All right, so do you end up with moisture in assemblies? Let's talk about this real quick, because this seems to be one of the biggest questions and concerns from last time. Was I talked about there, you need to calculate your dew point, but I didn't show you how to do it, or how it, or the who, what, where, and why. So let's talk about this, right? We have these walls, and we have a lot of things that we're worried about in those walls. Why do we need these barriers, vapor barriers and weather resistant barriers, and all of these things that we need on their air barriers? We want to control rain, right? We're going to control water intrusion. That's like a sprinkler or rain or whatever. We want to control that. That's easy to see. And so we can picture how we're going to control that. We want to control air leakage, right? We have to have a continuous air barrier. Wherever air can get into the assembly, so can moisture get into the assembly. So we want to control air for multiple reasons in the code. Then we have to control our indoor relative humidity, right? We do that through mechanical ventilation, different ventilation strategies. Maybe in certain climates, we have to add some dehumidification, right? So when to control indoor relative humidity, we do that through ventilation. Control construction moisture, right? Make sure that your building materials are dry before they all get enclosed. So we want to make sure that we're doing that. And then the one thing that I think is the hardest thing to comprehend, and it's because we don't see it, is the vapor. So we have this vapor that can get into the walls and wet, and we need to be able to wet and dry, right? And so how do we control that moisture in the wall that we can't see very much or feel very much sometimes? So while they're all interdependent, the controlling the vapor is huge. So I love this construction instruction. I think I talked about it last time, constructioninstruction.com. They have a great website. They have a free app that is amazing that you just download on your phone, and it shows you how to do windows, how to do walls, how to do everything, and how they're testing everything and anything moisture, vapor, thermal. Construction instruction is great. But Justin there had put out this great way of telling this. I got their permission to walk you through it. So this is for climate zone 4, but the concept is the same across climate zones, right? We have this wall. If you insulate it, we have this idea that if you insulate a wall, that it reduces the heating and cooling costs in a building, which it can if it's done correctly. And that it makes your building more comfortable. It can be done, right? But the reality is that most of the time we have too little insulation or too many leaks, and so moisture can get into the building. So what we're trying to do is look at how we put an assembly together, how we put a wall together, and see if all the layers, are they done correctly, and does it handle moisture, vapor, air, all of the things that it's supposed to be controlling. So we do what we call a dew point calculation, right? If it's going to be hot outside and I'm cooling my house, or I'm heating my house and it's going to be cold outside, wherever, when hot meets cold, moisture is going to happen, right? Take that ice cold soda out of the cooler and put it on the counter, and you're going to start seeing the moisture on the outside of the can, right? When the hot meets the cold. And so what we're trying to do is figure out how to move that dew point so that it's not right smack in the middle of the wall, ruining the insulation and ruining the framing. How do we do that? It's taking your climatic, the design parameters for your climate, right? And making sure, what are they? What is your mean daily temperature? And how are you going to build your wall, right? So if we look here, let me put this up here, right? This graph illustrates the potential for condensation and where it can occur for your wall, right? So the dark blue line is your mean annual temperatures. This is telling us that from about November to about March, we have the ability, we drop below this dew point. And so we have the ability to get condensation in our walls during these months, right? And so then the light blue line is how we built our wall and the temperature of the wall. And this example is, I have a 2x4 wall with R13 insulation. So I have this R13 insulation in my wall. That's still not warm. That's not got my wall warm enough to where I will not get condensation. So from about late November, early December, all the way to mid-February, I'm going to have condensation in my wall because I didn't add enough insulation to bring it up above that dew point, right? So what that's telling me is I need to add a little bit more insulation or build a different wall, right? And so you take that same wall in climate zone 4, R13 2x4 wall, and add an R5. That's just enough to keep me above the dew point, right? So now my condensation is going to be out here somewhere condensing in the air. It's not going to be in my building assemblies. Right? And so that's what the dew point calculation is. The code is not going to get into this. Can you imagine the code book if we had to design everything? We're not in the design phase, right? And so this is really a designer's requirement to really calculate their walls and make sure they're putting, the code is a minimum, but there's so many different materials and so many different ways to construct a wall. We could not make a code book big enough to cover every single scenario. So have to let the designers figure out, what are you using? Now you go calculate this dew point of this wall and make sure. Right now, if I'm in a colder climate, this is climate zone 4. So if I'm in a 5, 6, 7, I'm probably going to have a little bit bigger curve here, and I'm going to need a lot more insulation here to have this to bring the same thing above my dew point, right? And so that's what all these calculators are out there. There's a bunch of them. If I go to there's Applied Building Tech, Construction Instruction, Building America Solution Center. All of these places, these are just a handful of them, have a dew point calculator. You tell it how you're building your wall, what climate zone you're in, how you're building your wall, and what's your outside layer, what's your inside layer, what your framing is. And it will calculate that temperature of that wall and where that dew point will lie, and if you're safe or not. And so that is something that every designer should be doing. It's not up to the code official to do that for the designer. We're not supposed to be designing these buildings as code officials. In fact, the code tells us we're not allowed to, right? And so need to make sure that that is happening, because we have more and more materials and more ways of doing it. The code provides tons of options. And so we want to keep that flexibility, but that means this is going to be more reliant on the designer to go figure out what's going to work and what's not going to work. There's also this great Joe Stiebrook with buildingscience.com. He put out this great series of videos on how to build the perfect wall. I think a lot of people have heard of that, how to build the perfect wall. And he talks about how every single layer goes together, thermodynamic, moisture flow. He talks about everything. And so residential walls and commercial walls and all of that. I was going to show you a video, but it's you're not going to be able to hear Joe. And in order to get everything out of the video, you need to be able to hear Joe's voice, because he's comical most of the time. But he just goes through this, it doesn't matter what your insulation is, what type of insulation is cavity, or what type of insulation is continuous. What matters is how all the layers go together and that they're installed correctly, and that you have all of your barriers intact, your moisture barrier, air barrier, vapor barrier, water resistive barrier. That they all have to be intact, your thermal barrier. And so making sure that they all go into place is what matters. No, you don't have to say, oh, this is the best cavity insulation or this is the best continuous insulation. It depends on how they all go together. And so it's not product specific, it's application specific. So we won't go into that. All right, let's cover thermal bridging real quick. So let me just look here. Will you cover the ratio of external insulation to internal insulation and how it's related to dew point? I can't cover that too much. If you go into those calculators, it's going to depend on where you're at and the temperature, your relative humidity, all of that, versus how much cavity insulation and how much continuous insulation it's going to take there's too many variables, right? What is my framing? 2x4, 2x6, metal, wood, concrete? What is that? What, what am I doing? Where am I doing it? And so to get that ratio, that's going to be up to the designer, and you can go into those dew point calculators and put what you want to do, and you can play around with it. It's like I always say, if you're going to do something with a thermal envelope or go into ResCheck, play around, see how much adding a continuous changes your passing or failing, or how much cavity changes passing. Do the same with your dew point calculator. Get it to the point where you play around with it and figure out what will work for you. I can't get into a lot of that. Maybe that's a completely different webinar that we could do just for designers on calculating dew point. It's a good idea. All right, let's talk thermal bridges. There's all kinds, just like there are all kinds of bridges. The whole idea of a bridge is to get you from here to there, right? To transport you from here to there. The same is true for a thermal bridge, right? It transfers heat from one side of the assembly to the other. That's a thermal bridge. There are a lot of places that in our thermal envelope that happens. There are a lot of different kinds of thermal bridges. Some of the things that we need to think about is we take a R19 bat. It's R19 until we install it in something. Once we install it, then we change the U factor or the R value of the whole wall, right? So I think this is interesting to see that an R19, effectively, that wall is not R19. Effectively, it's 7.1 when you put it in between metal studs. There's a little less loss in with the wood studs, and so it's effectively an R16 wall, right? And so just because it says R19 doesn't mean it's R19. The code knows that when you tell it how you're installing it, like in a ResCheck or a performance software or whatever, we know, or in the prescriptive tables, we know if you're going to install it in wood, here's the value we need, because overall, this is what we're going to get from that wall. And so it knows that going in. There's a lot of thermal loss at that wood and at that metal when it comes to framing. So it's amazing to see wood lost between 14 to 18%, and metal reduces the R value of the wall by about 63%. That's why even in CommCheck or something, or in the commercial tables, you always see whenever you have metal in the building, you have to have 2 layers of insulation. And if you want to trade off 1 layer, that's fine, but you're going to have to do a lot, because you have to make up for the fact that you don't have that second layer of insulation in there. But there's thermal bridging. There's all kinds of thermal bridging that's taking place, and so the code has started covering it in commercial thermal bridging. You have to calculate your thermal bridging. I have a lot of jurisdictions now that are amending the residential code to bring thermal bridging requirements in for residential buildings also, to just make sure. I have like this. I think this is a good example. I have this heat loss because I have this floor that has this thermal bridge all the way through to the exterior. So I have this heat loss through my building. Whereas if I would have just put a thermal break right there, I don't have a heat loss, I have heat. I want to pay for the heat. I don't want to pay for the heat loss, right? And so the whole idea is, how do I keep the heat in the building if I'm trying to pay to heat the building, or out of the building if I'm trying to cool the building? And so there are a big, huge portion of that is floors, but we'll look at a few different things. So you have different kinds of bridges. A linear one, some part like a floor, that intersects the building, that forms this line all the way across. It might be a line up and down, like a Z channel, right? That's a linear thermal bridge. It forms a line along the length of a building surface, usually associated with the intersection of building thermal envelope assemblies and components. They aren't accounted for in the U factor. That's why you're going to start seeing more. That's why we had to start adding more and more things about thermal bridging in the envelope, because we weren't calculating the loss along this whole line of the building for our U factor. We calculate the U factor of the wall, but not the thermal bridge right there. And so it's not counted for that. That's why the code brought it in. Residentially, the code hasn't brought it in unless you've amended it. But it's good to know that you have this loss there. And so there are, it's usually like slab floor, balconies, corners, parapets, window to wall interfaces, all kinds of things where you have this linear thermal bridge. And so it can be accounted up to 20 to 70% of the heat flow loss, or the heat flow in the building. Can you imagine losing so much? That's why the code is like, we've got to cover this. And so some different ways, there's a lot of ways to mitigate that thermal bridge. One would be have your floor stop at that wall and build a new floor outside of it. Don't have a balcony that goes all the way through or a slab that goes all the way through. You're going to start seeing more and more and more of these places where you build separate components, right? Or you can, there are a lot of different ways you can put some continuous insulation. There are some proprietary things out there. Let me show you a couple of things. So you're going to start seeing suspended or separately supported balconies, right? Instead of balconies that go all the way through. That's one way of doing it. You can see there's all kinds of different places that we have linear thermal bridges. You can start seeing different proprietary things being made, maybe thermal blocks. We start seeing thermal blocks. We start seeing things like this, where you have these proprietary things where you have a block there that's got some R value to it, or at least a thermal block. So then you can, if you insist on doing a continuous floor, you can. Or if you're going to have metal to metal, you can have a thermally blocked a structural thermal block there. You can use materials now that are maybe not, it's just not solid metal, but it has a low thermal conductivity built into it. So there's different materials that can be used. But these are the things that on commercial buildings you have to start identifying on your plans. But residentially, unless you're a jurisdiction who's amended it, like Aspen, Breckenridge, places like that have brought this in for their jurisdictions. It doesn't mean just because it's not in the code doesn't mean it's not a problem, right? And so you also have point thermal bridges, right? That occurs at a single element or a discrete point, like maybe a fastener, which is a small point thermal bridge, but it also might be pipes or beams or columns that penetrate the building envelope. It decreases the U factor from 1 to 40%, depending on the amount of that thermal bridge. Some ways to do that is mitigate penetrations. Don't have a bunch of penetrations through the thermal envelope, or use low conductivity materials. Encapsulate it with at least 2 feet on both sides with insulation. Use better materials, and there's some proprietary things. Then you also have clear field thermal bridging, right? That's like the whole wall, the whole field is, you right here, you can see a good example. Here's one. This just has R13 thermal bat or R13 bats, and so you can see all of the thermal bridging that's happening, or the heat loss that's happening here. I cover that with just a 1/2 inch of rigid foam, and look at the amount of loss that of heat loss that has gone down. I don't see that anymore, right? So just clear field thermal bridge mitigation would be install some continuous insulation, right? Maybe using the right fasteners. They have different fasteners that instead of being full metal, maybe they have a metal for only part of it, and then they have a plastic sleeve that's using a low conductivity material, right, for doing that. So there are different ways to mitigate all of these thermal bridges. There's a great resource at that continuousinsulation.org where you can go in there. I love this resource. It's a design tool for steel wall or wood walls. Right, you go in and tell it what code you're trying to comply with, what climate zone you're in, what kind of cladding you're using, the R value of your exterior insulation, what kind of exterior sheathing you're using. It's calculating a bunch of different things. The performance, the thermal performance of your wall, right? My code requirement is this in this climate zone. Here's what I'm doing. I pass, right? Here's my vapor control. All right. It's calculating based on how you built that wall. Here's my vapor control. I'm not meeting a class 1. I'm not supposed to. It's not permitted, right? But I can use a class 2, and I'm meeting class 3, whatever. And it gives you all of a bunch of different ways. It's not necessarily calculating too much dew point, but it's a great resource in there at continuousinsulation.org. This, I think we went over this last time, but maybe not. This is just saying there's a difference between an R25 wall and an R20 plus 5. When you're talking about insulation and continuous insulation and the values of continuous insulation, you have to keep in mind that R25 just means I have an R25 bat probably in the wall, or an R25 cavity insulation in the wall. An R20 plus 5 means I have an R20 cavity, but a plus 5 continuous. There's a big difference by adding a layer of continuous, right? This could be R25 and still have all this thermal loss. This is an R20 plus 5. That's very different, right? And so you can see if you calculated all the layers, the effective value of the wall, if it was just R20 cavity, it'd be 17. If it's an R25 cavity, it's R19. But an R20 plus 5 gives me an effective R value of R22 because I've mitigated the thermal bridging. So it's huge. It's also why we need to shift from looking at just the R value to looking at all the layers of the assembly and what is our effective end result of that wall going together. Right. And so some good points there. All right. This is another great resource I wanted to get to you. Make sure that you are going here. This is a good publication on thermal bridging building, and it has a lot of great things in there, how to account for it if you want to calculate the U factor or as part of your wall. If you're in commercial, it does make you account for that. And it gives you a calculation in there. And so it gives you that, but it also gives you it gives you all the different ways to mitigate thermal bridging at different places, and gives you these great things like here. This is a bad way to do it, just to have a continuous floor through it. Here's a regular way that we start to see it. Here's a better way. Here's the best way, right? And it gives you that for floors or for glazing transitions or for parapets, or so there's really good resources in there for you. Another good resource, probably one of the first ones that I started reading was from Shock, the Guide for Analyzing Thermal Bridges. It gives you a technical handbook you can download for free if you just look for you just Google Shock's technical handbook. It's a really good one too. There's a lot of resources out there. I'm trying to say, it would be hard for the code to cover it all, right? So you have to utilize your resources. There's a lot of R values out there prescriptively. You can see we have a lot of different climate zones, and you have a lot of different prescriptive requirements. I would love to just understand from you what you're seeing the most of. Are you seeing continuous insulation being used? If not, why? If we have some time, you can type it into the chat. Otherwise, it would be great if you just email me. I would love to hear it. I will go straight to the insulation industry. We did this a couple of years ago. People were saying, we don't use it. Why? And they gave me lists. I had to go to the continuous insulation industry, the foam sheathing industry, all of them. And they sat and listened to a 1-hour presentation of why code officials or designers are refusing to use continuous insulation. And most of it was about resources and not understanding. And man, did they answer with their great, amazing continuousinsulation.org resource and applied building tech and all. They came out with all these resources. So if you're still having trouble, I want to hear about it, because we can go to this industry and say, you got to help us more. Here's some more things that we need that would help us do our job. And so let us know what those are. Buildingscience.com is great on showing you how all the layers should go together. Continuousinsulation.org, construction instruction. They have that free app that you can download that's pretty cool, that walks you through all kinds of things. And so Building America Solution Center, another great resource. And a huge, great resource, as Erica mentioned earlier, is the adoption toolkit, right? It has so many resources in there, all our webinars and all of lots of how-to guides in there on checklists and details for your plans and all kinds of wonderful things in there. So please be sure you're checking out that toolkit for that. I could probably talk continuous insulation all day, but that's what we have. I got an hour, and so there you go. That's what I have for you. So I would love for you to email me here at this and let me know more of your concerns, questions, things that you're seeing, so that we can cover it more as we move forward.
Perfect. Thanks, Shauna. Yeah, and your post-training survey will pop up. If you guys have any questions or comments for Shauna, I can also pass those along too. So, all right, we do have a few questions. If you've got a couple extra minutes, Shauna. Okay, I'm sorry, I had to step away for a minute. Did you answer the percentage-wise question? How much does interior? You did. Okay. Thank you. Can you talk about methods to ensure continuity of the continuous insulation between the underslab insulation and wall insulation?
Underslab and wall, the continuity. So that's a tricky one. A lot of times when you can count it continuous, you have insulation under your slab, and then you have insulation coming down. As long as that insulation coming down comes down past the insulation going across, even though one's on the inside and one's on the outside, it can still be considered continuous, right? That's why the code says, if you have, depending on the edition of the code that you're in, if you have to have slab edge insulation, and maybe it's a heated slab, so you have insulation under the slab and insulation at the slab edge, it'll tell you do your R10 and or R15, depending on where you're at. And it says if you have insulation under the whole slab, you only have to take that insulation down the depth of the slab, because it will form a continuous insulation. It's like the option, you have the option to insulate down and under. This is basically the same. You can go down on the outside and under on the inside and still have it be continuous, because you have no real thermal bridge there, right? There's no air taking place. So the code does allow that. Is it the best? I would take it probably a little further down than just the depth of the slab, so that it covers at least where the two insulations would line up if there weren't a wall right between them.
We might even have some details, like architectural details,
so.
that
and another good place to look is if you go into ResCheck. You don't even have to use ResCheck, just go into their help menu. They have a lot of good pictures of how you are allowed to calculate it and not what doesn't count. But they have some good pictures in there about how to call that continuous.
Perfect. All right, just stop the recording, and I